Yeah, good morning, everybody. It's 9 o'clock in Taiwan, and I think 9 o'clock in the evening, right, in Florida. Um, and we are very happy today. We have Professor Andy Dove from the University of Central Florida Department of Physics coming to give us a lecture on the. I think you have seen from the title about the interaction of the lander rover on the lunar surface with the regolith, and she will tell us about the detail. But the main thing is about that Professor Dove and her colleague Professor Carrie Donaldson Hanna, who will be giving a talk 1 week from now. They together they won a huge grant, huge for us, in Taiwan, but maybe not so huge for Americans.
It was pretty big for us.
It's great, and they are really doing the real stuff, for the lunar science for us to learn. Since we in Taiwan, we are just starting to do so, and so I think we had a lot to learn from them, and I hope that in future we have the opportunity to cooperate with University of Central Florida, because they have a huge program in space research and microgravity research and so on. It's a great place to cooperate with. I think that the main things about the lunar dust, you are also making some artificial sample too, right?
Yes, we have the XLith labs is housed here at UCF.
And selling them everywhere.
Yes, all over the world.
Yeah. Okay. Good. So we will listen to Professor Dove, her talk, telling us the very interesting research work she has been doing. Thank you. Yeah, please.
Thank you for having me. So yeah, thank you so much for the invitation to speak with you today. I'm excited. I've looked at the whole list of speakers who have given all sorts of amazing talks previously, and so I'm excited to sort of expand on a few different topics that I think have been touched on slightly before, and talk about some things that are of interest to me. Partly, these are of interest to us generically in the community, but also I have special interest, as you mentioned, because of their relevance to the LunarVise mission and our interest in exploring certain areas on the lunar surface. So I'm Addie Dove. I'm an associate professor at the University of Central Florida, and my main research interests are in dust and regolith interactions with planetary surfaces and charging of dust and spacecraft. So today I'm going to focus mostly on talking about some differences that we see and some things we're interested in with landing on the lunar surface. And I have this slide in here from when I've given some public talks, but I like to have it as sort of a reset when I'm talking anyway, because it's one of the really important things to think about when we're interacting with and landing on other planetary surfaces is the vastly different gravity regimes. And so we were talking a little bit before I started about the fact that a lot of the research I do and we do here at UCF looks at how regolith or dust behaves in microgravity. And that includes places like the moon and Mars, where gravity is significantly less than that here on Earth, and obviously then also on asteroids and Phobos and Deimos and other moons, where the gravity is just so much less that actually the way we think about the physical processes is very different than what we see here on Earth, where gravity dominates a lot of the interactions. And this has to do with of several of the different types of interactions I'll talk about a little bit today. So I know everyone knows this, but I like to have a few nice pictures of regolith to set us off. So again, a lot of what I'll be talking about today is the uppermost surfaces of planetary bodies, specifically the moon, which is covered in regolith that has built up over time due to bombardment and all sorts of different processes that take large rocks typically and break them down. And I am sort of loosey with a lot of the terms that I'll use, whether I'm talking about regolith or dust. Typically, dust and fines are sort of the smallest portion of the lunar regolith, and there are also things that are on the scales of millimeters and centimeters. and greater on the surface that are affected by these processes, but a lot of times I'll sort of lump that all together, and I'm mostly talking about the really finest portion of the material on the lunar surface. And this can be anywhere from, like I said, millimeters down to submicron and nanometer sized particles. And on planetary surfaces, a lot of what we have for places that aren't the moon is spacecraft observations that reveal really complex topography. And we see this throughout the solar system, right? We see really complicated surfaces that have various particle sizes, particle size distributions, and various distributions on the surface of where those particles are. It's interesting to think about the moon. A lot of what we see on the surface is the really fines, is the fines that are built up over time, but on smaller bodies like asteroids, they're also relevant to what we're thinking about in terms of exploration. The processes that we're talking about happening on the surface of the moon might actually happen and affect surfaces, the surfaces of asteroids, but also deeper down. And so all of these planetary bodies have this regolith that's built up on the surface due to impacts, and it's moved around in a lot of different ways due to impacts, vibrations, or seismic sorting on some bodies, things like landslides or mass wasting, electrostatic motion, which I'll talk a little bit about. And then there also can be some thermal processes at work here. And these all act to create different particle size distributions and also to sort the grains and move them around on planetary surfaces. The other context then for thinking about the surfaces that we're looking at, especially the moon, and I know there's been some really great talks in this series about dust dynamics and the plasma interactions on the surface, are these really interesting charging behaviors that we get because of where the moon is and the fact that the moon and other small planetary bodies typically don't have atmospheres. They're airless. Or they just have a small exosphere near the surface. And this means that they're really exposed to the full charging environment that's governed by things like the solar wind and sunlight. And so this can create some really interesting charging on the surface and some really complex charging environments on the surface that are going to play a role as we're going to these surfaces and exploring. So they're really interesting in terms of understanding natural phenomena, and a lot of the questions we have in science and in sort of exploring the surfaces are tied together in how we're going to understand what already is there and then how we modify it when we get there, and how we're studying it changes those interactions or gives us insight into those interactions. And so there's a lot of interesting effects that can happen both on the day and the night side of the moon and at places like the terminator or in shadowed regions where you have sort of day and night juxtaposed. So this is a sort of classic image we have here, again, talking a little bit about this plasma environment that governs the overall charge of grains on planetary surfaces, and then also what we think of in terms of where we're going to have things like photoelectrons, what the plasma will be like above the surface, and how that might govern the behavior of dust grains. I'm not going to focus primarily on this plasma environment today, but I do think it's important for a lot of what I do to understand that context, because I'm going to talk mostly about different sort of mechanical and surface and gas interactions today that really modify the environment. But it's really important to keep that in the background, because those particle charges and where they're distributed on the surface are going to make a big difference as we're trying to understand how we are interacting with the surface. So generally today I'm going to talk a lot about what are called plume surface interactions or gas granular interactions. And these are sort of lumped together in the term PSI, although some folks don't like this. But basically, these are interactions that occur when probably rocket exhaust, but it can also be some other surface gas perturbation, interacts with planetary surfaces. So this is going to happen when we're landing or taking off from surfaces. It may also happen if there's different types of mobility vehicles on the surface that might be moving around. There's some interesting work that's being done looking at ISRU and how we might use resources on the moon and how that might be, we might be able to sort of move dust around for that. So these granular gas interactions or plume surface interactions are going to be a really big deal as we return to the moon and have especially as we have a sustained presence on the moon. They're interesting because they modify the surfaces that we're landing on, and we'll look at that a bunch here. But they also might cause damage and pose hazards to spacecraft around them. So if you're landing in all of the Apollo missions, for instance, where we landed everything very far apart, or even the more recent missions from a number of countries, those landings have generally been pretty far away from each other. And so they perturb their local environment, but don't have a lot of effect on other landed vehicles. However, as we're thinking about a more sustained interaction on the lunar surface and potentially sort of like a base at the South Pole, for instance, or multiple countries landing in multiple different areas, we are going to have to think about how we're moving material around on the surface and how vehicles might interact with each other. When we're talking about PSI, their behavior will depend on things like engine properties, gas properties, and especially the environment, which is a lot more what I'm interested in. And there's also big changes with scale. So I'll talk a little bit more about this, but this has to do with whether you're on the Earth doing tests of these things or on the moon. Very different scales in terms of gravity, different scales in terms of atmosphere or lack thereof, that really make a big difference in how we're studying these things. So as I mentioned, this is a really important problem and it's relatively understudied. And part of that is that problem of scale. So it's just hard to do a lot of the studies that are physically relevant on Earth. If you were to do the best thing possible, you would have a giant vacuum chamber that would sort of simulate really low moon vacuum, and then you would have a full scale like engine nozzle landing on the surface, but the sort of giant scale of that is pretty impossible to actually accomplish on the ground. So a lot of what we do is use data from previously landed missions on the moon and also do scaled experiments of different degrees here on Earth. This is going to be really important, as I mentioned, for the number of upcoming missions and being able to put some of those missions in context and also make predictions for how we're going to move forward in the future. One of the challenges of the sort of scaled versions we've done so far, and these have been done for application on Earth, looking at plume surface interactions on Earth, landing in like desert areas, for instance, looking at landings on Mars. It's been really important for all of the Mars landers that have had descent engines, for instance. And then also obviously on the moon. And so typically research on this has been done really centered around a specific mission. They would understand what landing vehicle they were going to have and what the engines and nozzles are, and they would use those parameters to do some tests. But there is a lot of really cool work that's been done more recently, and a lot of it's more numerical, looking at how we can do simulations of these things to understand the behavior on different planetary bodies. And so those numerical simulations are amazing, and so there's a lot of complex fluid dynamics and then granular mechanics models that are used to look at those interactions, but they need to be driven by physical processes that we've actually measured, so by empirical measurements of data from lab experiments or larger scale tests. And one of the great challenges in a lot of this is that granular materials themselves are a really, really tough physics problem. So it's just really hard to model how granular materials behave. And then you combine granular materials with gas flow, and it becomes even more complex. And then you can also combine that with charged particle interactions. And so it's a really, really complex environment. And I mentioned earlier that the landing assets can potentially be a hazard to other vehicles around. There's some data, there was some work done by Phil Metzger and colleagues looking at one of the Surveyor landers. So one of the Apollo missions landed near a Surveyor, and they were able to get a coupon from the Surveyor and bring it back. And they studied some of the scouring and the sandblasting of that coupon, and how they think that how those interactions occurred with the lander. And it was very evident from these studies that dust grains from the Apollo lander had blown and scoured the surface of Surveyor and had caused interesting like fractures and pitting and other issues. And I mentioned, sort of to tie it back really quickly to what I talked about at the beginning in these charging processes, there's such a wide range of physical parameters that we have to consider when we're thinking about plume surface interactions. They're everything, and there's sort of a lot of texts and lists here, but everything from gravity to how grains themselves behave with each other, their sizes and size distributions, their shapes, whether they are sort of singular or in aggregates and how those behave and are interacting with these plumes, as well as the relative charging currents to the surface, all make a big difference in sort of both the starting conditions on the surface and then how those are modified and interact with the landing plume when you land. So if you just have your natural plasma environment, all of the charging currents, as we talked about earlier, to the surface are due to things like solar wind, photoelectron, photoelectron charging, or secondary electron charging. Then as you have these interactions, you can have additional charging due to the engine plume itself. And then especially due to tribocharging, so where you're rubbing grains together or grains against different surfaces. This is what we generally refer to as tribocharging, where you can have charge exchange between different materials. This is a really interesting area of study in sort of other areas of granular material physics. And we're starting to try to understand that a little bit better now for lunar surface effects. Okay, so I mentioned that PSI can drastically modify the surfaces that we're landing on. Here are some images from Apollo, and this is by some work done by Phil Metzger and others that show that blasts from Apollo, which one of the things to really keep in mind is that Apollo were pretty big vehicles, and most of the CLIPS and other international missions right now are much smaller and are creating much smaller effects. But upcoming descent vehicles might be even bigger than Apollo. So it's interesting to think about sort of that range of scales of how much perturbation might be happening. But so images from Apollo show that particles as large as 10 centimeters or more were able to move. So you can see in the bottom right here, this yellow circle is indicating a small rock, a 10-centimeter rock, and it actually moved due to the blasting of the landing. It can also cause, we know that these landings scour the surface and can cause morphologic changes. You may get interesting erosion features that have to do with the layering and the compacting of the surface. So it's really important to understand as you're landing engine characteristics, how you're descending, and the surface topography. And then finally, PSI also drastically modify the surface in a huge surrounding area. So we can use orbital imagery, and Ryan Clegg Watkins and others have done a lot of work at this, looking at orbital data to see how the photometric reflectance of the surfaces have changed over time and what kind of blast regions we create by landing on surfaces. And this likely happens due to removal of fine particles and then changing the structure of the regolith. There's still a bunch of open questions, though, about like sort of why these brightness changes that we see actually occur. But we do know that they are different depending on the landing profile and the local topography. So now I think I have some images that will play. We can look at a little bit more of actually what some of these things look like. As I mentioned, we have data from the Apollo missions. There were descent cameras looking down at the surface as they were landing. It's interesting to think about the Apollo missions because those were manually controlled, so humans were controlling the vehicle, and they're using their own facilities and different types of sensors to land, whereas most of the small vehicles now are having to use autonomy, and it gets complicated by these dust plumes that are being blown up. We also obviously do this on Mars with the different Mars landers, and we've done it on asteroids. So this is a nice little video that's playing right now of the Chang'e 5 landing. And you can see that just before landing, we can go back a few seconds here, maybe not. But just before landing, you can see the plume blow away and sort of scour the surface. And this happens sort of just at tens of meters above the surface typically. And here's another video. I think this is from the Chang'e 4 landing, showing the descent to the surface. And then, as you can see there, you're starting to get a bunch of blown material that obscures the camera view. It's blowing material from right beneath the lander, but also as you're going along on the descent. And it really complicates when you're trying to land what you can see on the surface. There's a nice touchdown there. There have been, I was hoping for this talk that there would be some new videos from some of the CLIPS landers. However, because both of the CLIPS landers that flew recently with Intuitive Machines and Astrobotic had imaging and descent cameras for plumes. But unfortunately, neither of those got data that we're able to see yet, or really, neither of them got much data. This is in here just to remind me to say that we also do this on Mars, and you can see this is just a cute little image of one of the Mars explorers looking at the helicopter here and the Curiosity rover. You can see these really nice tracks on the surface. So these processes are important on Mars as well, and what I'm talking about today is really focused on the moon, but understanding how we can do these things on the moon is going to be important for Mars. That's just a superfluous video of ingenuity. And then when we've landed with Perseverance on Mars, you can see how much dust it kicks up. So this is very different types of engines and different geometries of engines. There's multiple engines in this landing, and Mars has a different atmospheric environment. And so the plumes you get here are vastly different than what we see in most of the lunar surface landing videos. So it's really interesting to think about all of this in context. And you can also see there are huge rocks, centimeter-sized rocks being blown up and potentially impacting on your vehicle. So it's a very dynamic environment as we're landing on the surface. And then finally, we have also done this relatively recently, on a couple of asteroids. We've landed and touched down and gotten some samples and taken them away. The profiles for the OSIRIS-REx and the Hayabusa 2 mission were pretty different, but they both descended to the surface and had some jet of air at some point, but then disturbed the surface. And so it's kind of fun to watch how that happens. And when we see these touchdowns, so this is from the OSIRIS-REx mission, when you see it touch down, creates this giant mess. And one of the things that is interesting to think about for that is, again, the really low gravity on the surface, but also as it's touching down here, it's getting its sample and then it's blowing some air out. So that air that it's blowing out is partially what's causing this massive amount of material to be relieved from the surface and blow away and come back at the vehicle. Okay, so there are a number of ways that we can study these interactions, and there's a whole set of tests going on right now at some NASA facilities looking at larger scale tests and larger scale interactions of how we can sample and look at plumes on surfaces. But I'm going to talk a little bit more today about some of the stuff we do in one of our labs here, which is look at how materials behave when exposed to a plume in microgravity. And this is primarily work we've been doing in a chamber in the lab, in our drop tower in the lab at the Hawking Center for Microgravity Research and Education. But there are a number of groups doing different scales and different types of tests in 1G with different types of materials and potentially coming up on parabolic flights. So it's a really interesting area of research. And again, as we're looking at how these gas granular interactions occur, picking which part of the scales you're looking at is really important. So if you're doing things on Earth in 1G, are you looking at variations in particle size? Are you looking at variations in how much the plume is going to perturb? So there's lots of folks working sort of in different areas of the parameter space. So here I'll show you some different examples of these interactions in both 1G and in microgravity. So this is work primarily done by Wesley Chambers and then Tyler Cox and Alex Nicola in the labs at UCF. So on the left in this one, we have the experiment in 1G, and on the right, we have an experiment in our drop tower. So these are the exact same setups for the two experiments. This is a cylindrical chamber about this big in diameter that has it's a solenoid that allows a plume of air into the top of the chamber. It's evacuated to sort of 1 torr, so low Mars, very high for the moon, but a low pressure. And that allows us to do a jet of air into the surface. And so you can see on the left, there it is the movie playing, you just have to sort of watch it. But there are fines that you can see that get blown up from sort of down in the material. But on the right, you can see that with this plume of air, you get big chunks of material flying up. And the only difference, again, between these two experiments is the one on the left is in 1G, and the one on the right is in microgravity. So this is a nice example of really the importance of thinking about how things are going to move and how things are liberated much, much differently on low gravity bodies than they are on Earth. These are centimeter-sized particles with some fines mixed in, because if you have centimeter-sized clumps of regolith, you're always going to have fines as things sort of fall off. But some of the important things to think about here are how the grains, the rocks here are sticking together, what kind of what kind of cohesion they have, how that's broken apart, what kind of pore space they have, and how that is governed by both the size of the particles, how they're packed, and then also, again, the gravity level. So I'll move on from this one because I've been looking at that same one for a while. This is the same set of experiments, a similar set of experiments, same particles, but a much longer plume. So the first plume was on the order of 10 milliseconds, and this plume is on the order of 100 milliseconds. So it creates just a lot more air. And so you can actually see there's a little bit of stuff happening in the one on the left. And more than the last time, at least, because we are putting more air and more energy into the system. And then the one on the right, you get this giant uplift of all the material, and it all falls back to the bottom again because it's in a drop tower and it smashes into the ground. But so we always get it settling back at the end. But you can imagine on an asteroid or on the moon, all that material that's flying up, just like we watched in the Tag Sam movie, would fly up away from wherever your interaction point is. We've done some of this work looking at a range of different types of simulants. So we like to do cases where we have spherical particles like glass, beads that are more directly compared with numerical models. It's much easier to do numerical models of spheres than of really complex particles like regular simulants typically are. And so here we just have an example of how some of the image processing we've done to look at both side views and top-down views of these plume interactions. And you can see on the left, you get a nice sort of ejecta crater. A lot of what we look at is as these plumes are forming, what's the shape of that crater and the profile of that crater, and where does the ejecta go? And you get very different morphology depending on the simulant you're using and the plume you're doing. And then we can, on the right, you can see we can look sort of a top-down view of what that crater would look like. This is another example of, again, those spherical beads. And you can see here, we get, as in that image on the previous slide, you get a much more sort of classic ejecta profile where you have a ring material and a crater that forms and a nice ejecta profile. We didn't see that as much with the centimeter-sized particles because there's much different, the gas interactions with the regolith occur much differently for those centimeter-sized particles due to their packing and just their size. But here you can see you get a much more classic sort of ejectocone and the nice crater in the center that again sort of gets ruined at the end because we are falling in a drop tower. Here's another example of that. So we can look at that again in 1G and in microgravity for these spherical particles. And it's a pretty drastic case, right? So we've seen this a lot. We've done a long time experiments in the lab with Josh Caldwell and myself and others have looked at slow impacts in microgravity into regolith. And we know from those that you do see vast differences when you have a microgravity environment versus on typical Earth gravity. But we can see here the same effects occur when we're looking at plume interactions. So I'll play this one more time. And so the idea then is that we can use numerical models to run both cases if you have the same conditions, but you sort of get rid of gravity in one to look at the behavior. And then you can scale that for lunar or Martian gravity cases. We've done this with things like quartz sand, glass beads, and then those CI or gay particles. And again, you see very different behavior. So the glass beads are 600 to 800 microns. The quartz sand is less than 75 microns, so very small particles. And then the CI or gay was that like centimeter size simulant particles that we saw in the previous image. So here's just an example of sort of the different types of behavior that you see in those environments. And particle tracking in this is uniquely challenging. Traditionally with ejecta stuff, a lot of what we do is particle tracking, but in these, that's pretty challenging. And again, a lot of this work was done by Wesley Chambers, and we are working on a manuscript for some of this. We've also looked at things like how far away from the surface the engine plume is. So we know from descent videos that you get much different scouring depending on how far you are from the surface. And some previous experiments have done systematic studies where you look at different heights of the nozzle above the surface, and the sort of the height to diameter of the nozzle ratio is a key parameter in folks who look at plume shape and plume behavior. And so you can see here with the nozzle much closer to the surface, you get sort of a much more concentrated cone of the plume, and it creates a sort of the classic ejecta. The important thing to remember that we are seeing here, right, is that these experiments are happening in vacuum. So when you put a plume of air into vacuum, it has much different collimation than on Earth in atmosphere. And so that's one of the things to remember is sort of what the shape of your plume is going to vary based on the pressure of the experiments you're doing. Again, just some experiments at different lengths of time. We can see we can make a variety of messes in our vacuum chamber. All sorts of scales of messes. I'm going to skip this one, actually. We already looked at that one. So here, one of the nice things, and this is the same one that we were looking at earlier, but sort of highlighting the fact that you can see, in addition to the large particles moving, you can actually see some of the fines up in the chamber that are tracing the flow of the gas up and out of the regolith. So you get the plume impinging into the regolith, and then fines that come back out, and you can trace that flow. I'll play it one more time for that. Okay. One of the things, I'm going to skip that actually also. But so some of the things that we look at then are sort of all of those different factors of things like gravity level and then pressure in the chamber. We're able to compare sort of that range of conditions. We're also able to obviously do a wide variety of different types of regolith and simulants in the chamber. We have a variety of experiments that were done in collaboration with some folks at Masten Space Systems, which is now part of Astrobotic, looking at some small scale simulant experiments that then they compared with larger scale engine experiments, and they would make big giant craters with a full scale hot fire test, and we would be doing these small things to try to look at a range of parameters and understand these plume interactions over a range of parameters. The other thing I wanted to touch on a little bit today, so moving a little bit away from these plume interactions, is an additional type of interaction that occurs as we're landing and moving around on the surface, which is rover and regolith interactions. So I mentioned earlier the different types of charging that can occur that will charge grains. When we're landing with engines on the surface, you're also introducing gas that makes, and some of that gas velocity can overpower some of the grain charging. But when we're talking about roving or walking or any mobility on the surface, most of that is going to be very mechanical interactions of the vehicle with the regolith. And so those will be interacting with this upper layers of the regolith that are charged. And there's going to be different charge states depending on where you are. And interacting with the regolith can create charge. We talked already about tribocharging a little bit. So this is where you have rubbing interactions between different materials or even the same materials can cause charge exchange. And so we think that things like tribocharging are going to be a really interesting problem as we start exploring the surface more and increasing mobility on the surface. The sort of classic picture of this is the rooster tails that were generated during some of the Apollo missions when they were driving the lunar roving vehicles around. And they were going at pretty decent clip. They were going at pretty good speed and would drive and cause sort of these fans of dust to come up off the surface. And those were mostly, I mean, you can cause that here on Earth as well. If you drive too fast in a dusty environment, you can cause, or spin your tires, you can cause these sort of fans of dust to come up. But on the moon, it's really interesting because once those grains are lofted, they ideally, if we were in a non-charged environment, would just settle ballistically. So you lift them up. There's no atmosphere, they're just going to ballistically settle. But observations have shown that there's actually differences in how long it takes to settle. And so that likely has to do with the fact that they were probably charged particles, both naturally and from the interactions. And then also that they're in a plasma environment. So they're charged and they're in some sort of electric fields. So this can cause really interesting dust dynamics as well. There was some recent work, recently published work done by Alicia Yao, who looked at these interactions with spinning wheels. I actually had done some predecessor work to this many years ago when I was working with Mihai Harani in the labs at Colorado, where we looked at if you spin some rover wheels, some sample rover wheels in different types of simulant, different types of dusty materials, you can kick up dust and have that dust fall into a Faraday cup, which can measure charge. And we can look at that to understand some of these charging interactions. I think this sort of Faraday cup concept and sort of these dust charging interactions are really interesting to think about in terms of how we study the environment when we're on the surface. A lot of what we're talking about for the plume interactions is using video data to sort of observe what's been happening. That's what we've done traditionally, and that's what most of the landed systems that are going to be going in the next couple years are going to have cameras to look at descent plumes, including the Lunar Regolith mission. But then once you're on the surface, there's also additional things you can do to study those interactions. And so once we start returning to the same place on the surface, there's a lot of interesting questions about what landed assets could you have that would be able to measure charge, or if you could deploy something before you land that could then be on the surface and measure charge as you're landing, how would you do that and what would you measure? So these are some really interesting instrument questions if you're thinking about going to the moon and returning to the same place, especially. So one of the things that we saw from these studies were interesting sort of charging. And one caveat of these is that they were done in air, in ambient conditions. They weren't done in vacuum. Previous studies with charging and these tribocharging interactions have shown you get higher charge, obviously, in vacuum just because you have these interactions and there's no way to dissipate the charge. But then also you can get charging of different polarities more than we see here. So could see from these studies that sort of the simulants charged similarly, both the JSC simulants charged similarly. You get a little bit more charging distribution with some of the carbonaceous material, which is kind of interesting. But the sort of one of the more interesting things from this, which ties to some other experiments we're doing, is that different materials of the rover wheels themselves will cause the charge of the grains to be different. And this has to do with the fact that if you have tribocharging and you're on the triboelectric series, different materials are going to exchange electrons sort of with different efficacy. And so you can see for PVC, there was very little exchange of charge. It's very peaked around 0 picocoulombs, but you get a much wider distribution of charge for nylon, and then rubber is sort of positively charged. So it's interesting to think about different materials that are on spacecraft and how they might interact with the surface. One of the ways we've been looking at that additionally is by an experiment we call ERIE. So ERIE is an experiment that we designed to fly in microgravity conditions on a Blue Origin flight, so on a suborbital vehicle, to look at tribocharging and charge dust behavior. And so we use an experiment that is based on some previous experiments that have flown to do impacts into dust in microgravity, where we saw that as the door was opening, and I think if I go to the next slide, we saw that as the door was opening to reveal a particle bed underneath, grains would sort of fly out. And we hypothesized that this was due to the fact that they had been shaken a little bit and so probably had some inherent charge, but then also as the door is sliding open, it's rubbing all those grains together and they're charging to different polarities and sort of repelling each other. So this is data from a very old flight. This is actually from a space shuttle experiment that flew. Josh Caldwell led, called Collide. And so we saw this, we were looking back at old videos and we saw this and we're like, okay, how can we study this again in a more controlled way? We've also partnered with folks at Kennedy Space Center who are interested in studying the tribocharging and different sensors to be able to measure the charge as that door is sliding open. So we developed ERIE to combine some of this work on the MECA instrument and the WESS instrument from KSC with our Collide experiments. I'm going to actually mute that. So this is the most recent flight we had of ERIE. It was a highly successful flight and the experiment worked really well. And we were anticipating seeing all of this material flying up out of the chamber, just like we did in that previous experiment, and we did not. We do see some material flying up, and you can see here that there's some chunks of material sort of flying up out of the chamber. But it's much more subdued. We get interesting chunks of material happening. So it turns out one of the things that happened on this flight was that this was on a suborbital vehicle, it was on a rocket. As it launched, the material that was in the tray there compacted, and we think it compacted away from this door that was sliding. So we actually don't have good contact between the door and the simulants, and so we didn't get as much of that tribocharging interactions. We do, however, have some, in this version of the experiment, have some, sorry, my cat just jumped up and might have her tail in the video, have some charged plates on the side of the chamber walls here, so that if we do have charged particles flying up out of the chamber, we can look at their trajectories and their motion and how they go toward the walls, and we can use that to infer the amount of charge on the particles. This is sort of the next step before you would put something like a Faraday cup in, is just looking at the charge particle motion in an electric field. And you can see some interesting behavior where charged particles move and clump together. And then also you can see grains that sort of like stick to the walls and stick up on here. But so this was a really exciting experiment. We waited a few years for it to actually fly. You can see some interesting sticking and clinging happening between this polycarbonate plastic here and the dust grains that are coming up. You sort of get some sticking back there. You have these clumps that come and stick on, this is just a glass face that we're looking through with the camera. So you can see these sticking on the glass here, but then you can see these particles here sort of nicely flying up toward one of the charged plates. So what we're working on right now is doing particle tracking and trying to understand this motion. There's a nice grain here that just sort of sticks and clings there, and it doesn't fall until we start to come back down and you get much higher gravity. So it's been fun sort of just watching these videos in slow-mo and seeing what the different particles are doing. And I have students that are currently working with me to analyze the particle motion. So hopefully we'll have some cool results from that soon. We did measure some charging. I mentioned we have little electrometers in the door as it slides open. We measured some charging. This is the sort of levels of charging we got during testing. You can see we have different materials, and so you get a wide variety of charge. However, in flight, we only had a small amount of charge difference. And this likely has to do with the fact that it wasn't in direct contact with the regolith. So we're measuring some charging, which is really interesting, but it's not in direct contact with the regolith. So we're thinking right now about what this charge means and how we interpret this data. So I'm going to wrap up there. I would love to talk about all sorts of other types of experiments, but and I'm happy to answer any questions about anything I talked about here or other questions you might have about regolith or dust behavior in microgravity.
Okay, thank you so much, Eddie. Very interesting talk. Any questions from the audience? Yeah, you could either raise your hand or just talk to the microphone. Chi-Hong, yes, we have a student, Chi-Hong Lin. Yeah, Chi-Hong.
Can you hear me, Professor? Okay, so since for your great talk, Professor, so you mentioned about that this kind of the particle in the surface, they are strongly affected by the magnetic field and the electric field of this moon or the asteroid surface. So my question is that possible that we can control the orbit of this green particle under the spacecraft through charging the spacecraft with the electric field or to set a magnetic field inside the spacecraft? I mean, it might be difficult for the old spacecraft because they consume many energy, but it might be a small problem for the modern spacecraft because modern spacecraft have a strong battery.
Yeah, that's an interesting question. I think so. Definitely, we could control particles with electric fields or with magnetic fields. One of the I think when we're talking about landing and sort of the magnitude of those big plumes, it would be a lot harder to do. But there are folks that are very interested right now in dust mitigation and how you would prevent dust from sticking to surfaces, or once dust lands on surfaces, how you might get rid of it. And so there are active techniques that use electric fields and standing waves and electric fields to move dust off of surfaces. And there are folks working on like magnetic wands to help remove dust particles from spacesuits and spacecraft and things like that. So there are definitely ways that you can control that. When you're looking at spacecraft, I do think it's interesting to think about like what the charge is of your spacecraft, because your spacecraft is also going to be charged based on the environment it's in. So if you can control that and understand how that's causing things to stick or not stick, that would be an interesting question.
Okay, thank you, Professor.
Yeah, thanks.
Any other questions? I want to ask a question that is from your talk, as if, if whenever you have dust, you will have a charging. And one of the fundamental problem in planetary science is about the origin of the solar system, about the planet formation in the solar nebula. As you know, it's just filled with dust, right, and gas. And but so far all this model have not taken into account the electrostatic charging of the dust.
Yeah. So folks who look at planet formation, so planets form, right? You have lots of dust grains that are different sizes, and we know that there are different ways the dust has to come together and accrete and then form bigger things. Some of the models of the very small dust grains in the models do include adhesion and different like van der Waals forces and some of those sort of small scale electrostatic effects. And folks that look at like Cassini data and Saturn's rings also think about the effects of electric fields on the structures that we see and on how ring particles might come together. It is interesting though that a lot of I think I'm thinking through this a little bit, and most of the models that look at aggregation and collisions do sort of treat them as uncharged particles though. Yeah, and like a lot of the laboratory work that's done is done with generally uncharged particles. There are some cool experiments done with like some dusty plasma experiments that I think are super relevant for this, but they haven't been done exactly in that context before.
Well, along the same line, for electrostatic levitation of charged dust, there's a problem with the cohesive force. And what would be your thinking about that?
Yeah, I think a lot about that. So we know that dust grains are charged. We hypothesize that there's electrostatic lofting on the surface because, again, you have these differences between different charge regions on the surface, and you have a positive grain, it can get sort of ejected and go to a more negatively charged surface. And there's been actually some more recent work looking at how you might need to overcome that cohesion and how we can measure the cohesion. I've done some work with some students looking at how we can measure sort of grain cohesion, or how we measure bulk grains pulling off from surfaces. And it's again one of these things where we have some models that show us that the cohesion might look something like this, but it's been very hard traditionally to match the models of like just cohesion with electrostatic lofting models. I think we're getting pretty close now. There's a number of folks working on some of those problems. And there's some cool experiments that have been done recently that are trying to address some of those.
Yeah,
I think that's an interesting question to like think about as we're going on the surface though, and as you have things rolling on the surface, like what does it take to pull grains off the surface, and how can you overcome electrostatic effects?
It's always a good question.
Yep. Yeah. How does dust move electrostatically on the surface is always a good question.
The tribal charging experiment you showed are very interesting, because you mentioned that I think you must know Sean Shu, right? Sean, yeah, because one time he saw us talk about his, your work on looking at the Apollo astronauts' wheel, picking up dust and to measure the velocity, and trajectory. Then, but the thing you're doing now, you said that one time you said that it's in ambient air condition, not in vacuum. Would that make a difference, in vacuum or in ambient?
Yeah, I think it'll make. Generally when we do experiments in ambient conditions, especially with charging, you lose a lot of the charge just because you lose it to air interactions, right? So, well, especially in Florida, but even in Colorado, you lose a lot of charging. So the other experiments and some of the stuff I've done, you do want to try to do things in vacuum if possible. For that set of experiments, just the setup was challenging to be able to do it in vacuum, but I think that they might be working on some of that now. If not, I should pick it back up again. But yeah, it's one of those interesting questions, and it's because you even if you're generating the charge due to the interactions in ambient conditions, between them being lofted and falling into the Faraday cup, you're going to lose some of that charge, or it won't be the sort of full set charge distribution. And you also just will inherently have more charge already on grains if you've been interacting with them on the surface in vacuum.
Yeah, how big the experiment would be, meter size or what?
Those were sort of a wheel that was like, I don't know, a few centimeters in size. You could do a large scale experiment with like a meter size wheel and kick up a lot of material. I've been thinking about that some with some experiments we have going on in the Exolith labs here. But I think it's interesting to try to like understand how we can measure the charge at different phases in that process.
Okay, anyone? If no, and I will ask the last question, a very important question. How many times you have been on suborbital flight?
Well, suborbital flights, I haven't been on any yet. But parabolic flights, which is the zero-G airplane, yeah. I'm hoping to go on a suborbital soon. My experiments have flown many times. I've been on parabolic flights for 6 flight campaigns, which I think is like 9 flights or something. So I have something like 2.5 hours in microgravity.
Yeah, because I saw a slide with you floating, you know, with some boxes, and that's amazing.
Yeah, we're flying again next week, hopefully. So doing some more experiments next week. So I'm looking forward to it.
Thank you so much. Thank you so much. It's getting late also in Florida, but we are just about getting to work. And then and thanks again. And we look forward to the next talk by Hannah. Yeah, Professor Hannah.
Yeah. Thanks so much for having me, and I'll be excited to see Carrie. Will talk about lunar bias, and I know she's excited to talk with you.
Best of luck for your research work. Thank you.
Thank you. We look forward to collaborating in the future.
Yeah, right. And by the way, I would drop you a note concerning the question I have about the UV spectrum, right? Okay.
Sure. Yeah, that sounds great.
Thank you. Bye bye.
Okay. Thank you.